All right, so let's start the problem solving session for chapter 14. Okay, so let's start with question number 1. Okay, so what we are given here and what it asks us to calculate. Let's see. Okay, so how much heat input is needed? Okay, so here it asks us to determine how much heat. Okay, so that's the unknown. And what are the given thing here? So it says that to raise the temperature of an empty 20 kilogram vat made of iron from 10 degrees Celsius to 90 degrees Celsius. Okay, so the first one is when the vat is empty, and the second one is if the vat is filled with 20 kilogram of water. Okay, in both cases we have to calculate the heat required. That means we have to calculate Q. Okay, so first let's do the first one. So Q vat. Okay, now we know that M, the definition is MC delta T, right? For here M is the mass of the vat, that is 20 kilogram. Okay, and C, it's made of iron, right? Now we need to know what is the iron's specific heat capacity, and I already have it. You can check the table in the lecture, and that is equal to 450 joule per kilogram per degree Celsius. And then delta T is the final temperature minus initial temperature, right? Final temperature is 90 degrees Celsius minus 10 degrees Celsius. Okay, so if you multiply all these three number, okay, I mean, if you do this math, you should get so I got 7.2 times 10 to the power 5 joule. 7.2 times 10 to the power 5 joule. Okay, so that is for the first one. And now second one. Okay, so second one is basically this one, the one we have already for the vat, and then we have to add the heat required for 20 kilogram of water. Okay, so let's first calculate separately for water, and then we can add them together. So for water, it will be MC water delta T. Okay, M is again 20 kilogram because we have 20 kilogram of water, and for water, CW, that means the specific heat capacity is 4186 joule kilogram degree Celsius, and this is again 90 degrees Celsius minus 10 degrees Celsius. Okay, so this is equal to 6.7 times 10 to the power 6 joule. Okay, so the total heat we need is Q vat plus Q water. Okay, so when there is water in the vat, the total heat we need is 7.2 times 10 to the power 5 joule plus 6.7 times 10 to the power 6 joule. Altogether, it is 7.4 times 10 to the power 6 joule. Okay, and this is the answer for the second one. All right. Okay, so now let's do the next one. Okay, so here we are given so if 200 centimeter cube of tea at 95 degrees Celsius is poured into a 150 gram glass cup, okay, initially at 25 degrees Celsius. Okay, so we have many things already given. So this is the volume of tea actually. This is the volume. Okay, so this is the volume of tea, and the initial temperature of the tea is 95 degrees Celsius. Okay, and then this is uh, the mass of the cup and the initial temperature of the cup. Okay, now here you see that when you put the hot cup, hot tea on the cup, so the tea is at 95 degrees Celsius. That means it is at high temperature, and cup is at lower temperature, 25 degrees Celsius. When the tea is on the cup, you know that the tea will be losing heat. Okay, it will be giving heat to the cup, and cup will be gaining heat. Okay, and because of the thermal equilibrium, at some point the temperature of the both object, I mean the tea and the cup, will be the same. Okay, and that temperature we have calculate. So what is the final temperature of the system, of these two systems? Okay, right? Now, there are many ways to calculate it. So we'll be using the conservation of energy equation. So you remember that conservation of energy is this one, Q equal to 0. Okay, sum of Q equal to 0. Okay, so here we have two terms. One is by T, another is by cup. Okay, so one is by T, another is by cup. Okay, so Q T plus Q cup. Okay, that is equal to 0. Now QT will be MT C water. Actually, T is almost water. Okay, so we assume it is the same as water. So the specific heat capacity of T is basically the specific heat of water. Okay, and then delta T. And the similar thing for the cup, M cup. Okay, and glass, so C glass, and then delta T. Okay, so this is the delta T for T, and this is the delta T for cup. Okay, now before we move to this equation, first thing is here the mass of the T is not given. Okay, instead the volume of the T is given. Okay, so we need the mass of the T. So how to determine the mass from the volume? Okay, so the equation we need here is this one. Okay, the density of water is equal to mass per unit volume. So mass is equal to density times the volume. So as we are given the volume and we know the density of water already, so we can multiply these two terms to get the mass of the T. So the mass of the T will be 1000 kilogram per meter cube. So this is the water's density, and V is the 200 centimeter cube. Okay, now centimeter cube, you know that's not the it's not the standard international unit. Okay, so we have to convert centimeter cube to meter cube, right? So what we need is 10 to the power minus 2 3 times. Okay, because we have centimeter cube. Okay, so centimeter to meter is one centimeter is equal to 10 to the power minus 2 meter. Okay, so using this you can show that you need basically 3 times this, and that is meter cube. So what we have here, if you do this math, you get the mass of 200 centimeter cube T is equal to 0.20 kilogram. Okay, so now we know everything, right? So MT is now this kilogram. Specific heat of water is 4186 joule kilogram degree Celsius. Okay, delta T for T. So final temperature for T we don't know. Okay, so that we have to calculate. Initial temperature for the T is 95 degrees Celsius. Okay, so you see that this is different than the change in temperature for the T is different than the change in temperature for the cup. So for the cup, it is this kilogram, right? The value is given in grams, so we have to convert it into kilogram. And for glass, the value we can take from the table given in the textbook. And delta T here is final is T, we don't know, and initial is 25 degrees Celsius. Okay. So you will see that the first term is positive, first term is negative because the final temperature is lower than 95 degrees Celsius. And that tells us that the T is leaving, the heat is leaving from the T, and the second term is positive, and that tells us that heat is entering the cup. Okay. So we'll be using these equations and solve it for T. This equation for T. Okay. Now, so we'll have 4 terms. Okay. So let me write down all the 4 terms and then do so. Minus so plus 0.15, then 840 T, and then minus 0.15, 840, and 25 equal to 0. Okay. Now you see that two terms, we have 2 terms that contains T, okay, and then 2 other terms are completely numerical. So if you simplify this, you should get something like this. So I got something like this, 963.2 T minus 8264, actually 684, and that is equal to 0. So T is equal to 82684 divided by 963.2. Okay, and that is equal to 86 degrees Celsius. Okay. All right. So there are some other way to you can solve these. Okay, so in the textbook, you will see that there are 2 methods they show, but I prefer this one. Okay. But yeah, I mean, no matter what method you use, if you get the correct answer, you get the full point. Okay. All right. The next one. So here, an engineer wishes to determine the specific heat. So here we basically use the calorimetry. Okay. So you want to know what is the specific heat of a sample. Okay. So that we have to calculate, and what we are given, the sample's mass, okay, the sample's initial temperature, Okay, and then it says that this sample is quickly placed in 0.4 kilogram of water, and water's initial temperature is also given, which is contained in a aluminum cup whose mass is 0.2 kilogram. Okay, so that means the aluminum cup's initial temperature is also 10 degrees Celsius. Okay, and the final temperature of all the materials, I mean the sample, water, and the aluminum cup is 30.5 degrees Celsius. So if so, what is the specific heat capacity of that sample? Okay, now here you see that the sample is very high, is the sample is at very high temperature, right? Now when you put the sample in the water, right, the sample will lose heat. Okay, on the other hand, the water and the aluminum cup will gain heat. Okay, now here we will have three terms. So in the last problem, we basically solve a similar problem, but there we had only two terms. Here we will have three terms. Okay, one for the sample, one for the water, and one for the aluminum cup. Okay, other than that, it's exactly the same thing. Okay, okay, so again, let's start from this equation, q equal to 0, and then we'll have q sample. Okay, and then q water, and then q aluminum, that is equal to 0, right? The three terms. Now for sample, it will be m sample, c sample. C sample we want to know what it is, and then delta t sample. For water, m water, c water, delta t for water. The same thing for the cup, aluminum cup, right? So it is m aluminum, c aluminum, delta t aluminum, that is equal to 0. Okay, okay, so we have to basically calculate CS. So let me solve it for CS and then plug the value. Okay, so it is ms CS delta TS, and that is equal to negative negative MW CW delta TW negative MACA delta TA. Okay, so CS is equal to negative MW CW delta TW negative MACA delta TA, and then here MS delta TS. Okay, now we have to just plug the values. Okay, so let's do it one by one. MW means the water. Okay, so water's mass is this. Water's specific heat capacity is this. And delta T for water is water initially was at 10 degrees Celsius, and final temperature is 30.5 degrees Celsius. 30.5 minus 10, 10 degrees Celsius. That's for water. Okay, and this is also for the aluminum cup. Okay, so the aluminum cup's mass is this one. Okay, aluminum's specific heat is 900 joule per kilogram degree Celsius, and delta T is the same thing for aluminum 30.5 degrees Celsius minus 10 degrees Celsius. Okay, so that's the numerator. Denominator is the sample's mass is 0.150 kilogram, and final temperature is this. Initial temperature is 540 degrees Celsius. Okay. Now, if you do the math in your calculator correctly, you will see the value of CS, I mean the specific heat capacity of the sample is this 497 joule per kilogram degree Celsius. Okay, all right. So here you see that this term is negative, and this negative will cancel the negative in the numerator. Okay, and that's why we get a positive value. So make sure you understand how I calculate it. Okay. All right. Let's move on. All right. So it's a very similar. This problem is also similar to the last one. Here we have how much energy does a freezer have to remove from 1 kilogram of water at 20 degrees Celsius to make it ice at 12 degrees Celsius. So we have water at 20 degrees Celsius. You know that if you want to decrease the temperature, okay, you need to remove the heat, okay, and the refrigerator can remove the heat from the sample. Okay, and how much heat we have to remove, that we have to calculate. Okay, all right, so the energy need to remove here is equal to the heat required to remove the temperature, I mean, the total heat we need is basically equal to the two heat, one heat, Q1 and Q2. Let me talk later. Actually, three heat. Okay, and let me talk one by one. So Q1 is the heat that this water, I mean 1.5 kilogram water, are I mean, to decrease the temperature of the 1.5 kilogram of water from 20 degrees Celsius to 0 degrees Celsius. So this is the same mass for all. Okay, so M will be the same for all the Q1, Q2, and Q3, and then C will be for water's specific heat, and delta T will be the final is 0 degrees Celsius and initial is 20 degrees Celsius. Okay, so this is the first term, and this term tells us the heat required to remove the temperature from 20 degrees Celsius to 0 degrees Celsius. So 0 is final and 20 is initial. That's why 0 minus 20. Okay, make sure the order, so the final minus the initial. Okay, and then Q2 is the mass times the latent heat of fusion. Okay, so you know that at 0 degrees Celsius, in this case, it will be freezing. Okay, so in the theory class, we see that it was melting at 0 degrees Celsius because we are adding heat, because here we are removing heat. That means at 0 degrees Celsius, the freezing is happening. Okay, so we need this term, and then again we need another term to remove, I mean, to decrease the temperature of the ice. So this water is now ice. Okay, and we need some heat to remove from the ice to decrease the temperature from 0 degrees Celsius to minus 12 degrees Celsius. Okay, so the first term is for the water. Second term is for the phase change, and third term is for the ice. Okay, now we have to use the specific heat for the ice, and the final temperature is minus 12 degrees Celsius, and initial temperature for this one for ice is 0 degrees Celsius. So again, make sure you understand the order. Okay, so here we have three terms, one for the water, another for the phase change, and another for the ice. Okay, now if you plug all this value here, now what we get? 1.5 kilogram. Okay, CW is 4186 joule kilogram degree Celsius, and this is minus 20 degrees Celsius, and then mass is again 1.5 kilogram. The latent heat of fusion is 333 times 10 to the power 3 joule per kilogram. Okay, make sure you understand this. Okay, and then again this is 1.5 kilogram. Sea ice is 2100 joule kilogram degree Celsius, and this is minus 12 degrees Celsius. Okay, now when you add all these three terms, you should get something like this: negative 6.6 times 10 to the power 5 joule. Okay, so that tells us that heat is removing. So I mean, heat is leaving the system. So minus sign tells us about that. Okay, so negative means heat is leaving from the system. Okay, all right, let's move on. So another similar problem, I mean, not a similar problem, it is similar to 2 and 3. Okay, so here what it said, it says that at a reception, okay, if 0.5 kilogram chunk of ice at negative 10 degrees Celsius is placed in 3 kilogram of iced tea. Okay, so ice here, and here we have water, and that is at 20 degrees Celsius. So we have two objects, one is ice, another is water. Okay, now at what temperature and in what phase will the final mixture be? Okay, so we have to basically calculate the final temperature. Okay, final temperature and in what phase it will be. Okay, here you can consider the tea as water and ignore any heat flow to the surrounding, okay, including the container. Okay, so we can use the this equation, Q equal to 0. Okay, now here when you put the ice in the tea, okay, so the tea will lose energy because it is at higher temperature than the ice, and ice will gain energy, right? So Q ice plus Q water. Okay, now Q ice will have several terms, right? Why Q ice will have several term? Because ice is at 10 degrees, minus 10 degrees Celsius. So we'll have one term to raise the temperature from minus 10 degrees Celsius to 0 degrees Celsius. Okay, and then at 0 degrees Celsius there will be phase change, and then from 0 degree to some final temperature. Okay, so for ice there will be three terms, and for water there will be one term. Okay, so for ice there will be 1, 2, 3, similar to the last problem. Okay, so in the last problem heat removes from the system, and here heat will adding to the ice from the water, okay, from the tea actually. Okay, so okay, so first term, so this the parenthesis is for the ice. Okay, so first term is this. Okay, and then ice's ice's specific heat is 2100 kilogram, sorry, joule kilogram degree Celsius. And then for the ice, the final temperature is 0 degree Celsius minus 10 degree Celsius is the initial temperature. Okay, so this is the first term, and then the phase change will happen, and then phase change means this times okay, this kilogram, and then 333 times 10 to the power 3 joule per kilogram. Okay, and then the last term for the ice is again this kilogram, and this time the ice is basically water, so we have to use this term. Okay, and here the final temperature is, we don't know, the initial temperature is 0 degree Celsius. So these three terms are for the ice, and for water or ice we'll have 3 kilogram and then 4186 joule kilogram degree Celsius. Final temperature we don't know, initial temperature is 20 degrees Celsius. Okay, so we have many terms here. Okay, so let me write down. So the first term will be something like this: 0, 5, 2, 1, 0, 0. And this is basically minus, and minus is plus, so it is 10. So this is simple. The second term is also simple. Okay, third term is also simple. Okay, that is just T. And fourth term is basically two terms. Okay, so now we have to write two terms for water, one for T, another for 20 degrees Celsius. So 34186 T and minus 34186 20, that is equal to 0. Okay, so now we have 5 terms. 2 terms contain T, and all the other 3 terms are numerical terms. So if you plug all these values in your calculator correctly, you should get something like this. Actually, I did all together. So what I got, final value T is equal to 5.1 degree Celsius. Okay, and this tells us that the final phase is the liquid phase. Okay, okay, final phase is liquid because at 5 degrees Celsius water is water basically. Okay, if it is less than 0 degrees Celsius, then it is ice. If it is higher than 100 degrees Celsius, it will be steam. Okay, in between 0 and 100, it is water. Okay, so that means it is in the liquid phase. Okay, all right. All right, so this is a conduction, the rate of heat transfer by conduction method. Okay, what we are given. So we have to calculate the rate of heat flow. Okay, rate of heat flow, that means Q over T we have to calculate, and we are given the area, cross-sectional area, thickness, okay, and the temperature between the two ends. Okay, and this is a glass, and for glass we know the thermal conductivity from the table. Okay, so here is the equation: Q over T equal to K A T1 minus T2. So T1 minus T2 is the final, the higher temperature minus lower temperature, and then it is divided by the thickness. Okay. So what we have, so from the table we can have this value for K, that is 0.84 joule per second per meter per degree Celsius. So this is the value of K. The cross-sectional area, so 2 times 1.5 is 3, right? 3 meters square. So this is A. And then T1 is 15 degrees Celsius minus 14 degrees Celsius. That means it is 1. And the thickness is 3.2 millimeter. So millimeter means 10 to the power minus 3 meter. Okay, 1 millimeter means 10 to the power minus 3 meter. So if you plug all these values in your calculator correctly, you should get something like this: 788 watt. Okay. All right. And this is the last one. Okay, and this is the here we have to calculate the heat transfer rate by radiation. Okay, so it says that an athlete is sitting unclothed in a locker room whose dark walls are at temperature 15 degrees Celsius. Okay, so the room temperature is 15 degrees Celsius. The person body temperature is 34 degrees Celsius. Emissivity is 0.70. Okay, and area of that person's body is 1.5 meters square. Okay, and we have to calculate the rate of heat transfer by this athlete. Okay, the rate of heat loss by radiation from from this athlete. So how to do that? So remember that this is the equation. So sigma, and then T1 to the power 4 minus T to the power 4. Okay, so here T1 is the body temperature and T2 is the room temperature. Okay, surrounding here. So before you plug the value, make sure you convert the temperature in Kelvin. So 34 plus 273, and that is equal to 307 Kelvin. T2 is 15 times plus 273 is 288 Kelvin. Okay, so that is very important. Many students forget to do that. Okay, now epsilon is already given, that is 0.70, and that is the Stephen Boltzmann's constant. We can get the number from the textbook, and that is this. Okay, the area of the athlete's body is 1.5 meters square, and then T1 is 307 to the power 4 minus, okay, so Kelvin to the power 4, and then 288 Kelvin to the power 4. Okay, so if you plug all these values correctly, you should get a value equal to 120 watt. Okay, so the rate of heat loss from this athlete is 120 watt. Okay, so that's we have for this chapter. Okay, in the next lecture I'm going to start chapter 15, and there you will be learning about the thermodynamics laws. Okay, so that's it for this lecture. I will talk to you in the next lecture.